All right, good day, everyone. What we're going to be talking about today is going to be how we do a linear regression, a power regression, and so forth. Okay, so basically, our goal is to be using technology or a calculator to actually um, create an equation based off the information we have. Okay, so let's just go through a couple of things here. So the problem they give us to start with is going to be basically how long or how fast can a car be driving, and how long does it actually take to brake based on that speed. Well, the thing is, whenever you get data similar to this, for example, speed and braking time, there's not going to be any set value. Okay, it's very hard to have a set equation just based off of that. Okay, so what we want to do is be able to take the data that we have here and turn it into an equation. Okay, so we want to use technology to our advantage to help us out here. Now, as you can see, these are all the speeds based on, or this is all the braking distance based on the speed. For example, at 20 miles an hour, it takes you about 20 feet versus 65 miles an hour, it takes about 220 feet. Now, the main idea that we want to understand is first, how do we actually set up a regression? Well, if I want to set this up as a regression, I'm going to go to the calculator. I'm going to hit Stat, Edit. And notice how I plug all those values in. L1 is my X values, L2 is my Y values. Okay? After I take that step, I go back to Stat. I go over to Calc. And since I want a linear regression, I'm going to hit Lin Reg. I'm going to make sure I have L1 and L2 in my X list and Y list. And then once I work it out, I end up getting my set equation. So the linear equation for this is going to be, Y equals 4.41x minus 90.04. Okay. However, we kind of run into an issue here. Okay. That is a linear equation based off this data. Truthfully, we don't know what type of equation it is. For something to be linear, it needs a constant rate of change. And unfortunately, if you look at these problems, there really isn't a constant rate. In this one, you go up by 8. From here to here, you go up by 12.5. And each time you get kind of a different or increase in how much you're actually going up by. Okay? All the way to the point where you're down here going up by 18. So we have an issue here. Now, we could even graph this out and see that same issue, of which, if you notice here, if I were to graph this out, notice how this chart isn't a set line, okay? It looks more similar to this, right? A curved function. So now it's up to me to kind of determine, well, how am I going to actually come up with an equation? Well, let's just say I wanted to use a linear equation still. Okay, but for me, I look at this as like an exponential function, something that starts small, but then gradually increases as we go up. Well, one way I can do this is I can simplify a lot of my work by taking the log of each side. If it's an exponential equation, I can simplify it by taking the log of each value. So what I did here on number 3 is I literally went through and I took all these values and I did log of 20, log of 20 to get what's on the right-hand side. Okay? The reason I'm doing that is because if I take the log of a specific answer, as long as I keep the same base accurate along the way, then I should have the answer as an exponential. So all these answers here are my exponentials, which is kind of what we were thinking from that graph in the first place. On top of that, when we graph it out, it does start to kind of look like a line, right? This function does look very similar. If I were to actually pull out a line here and try to create one, I do get pretty close to actually getting a set linear equation. Okay? So we're kind of onto something here. So what we're going to do now is we're actually going to create an actual linear equation based off of this. Well, I'm going to go through the same process, but instead of wasting your time and going through it, because you can always go back in the video and watch how to do a regression, what I would do is I would plug these values in and use a linear regression on them. Well, if I were to do that, I would get this equation here. Okay? This is after I would use a linear regression. Okay, and I get this equation. However, we still run into an issue, right? Because we've talked about this before and how in the first problem, this really wasn't linear. okay? So even though I took the log of each side, I don't care about these numbers here. I want the equation for these numbers over here. So what I need to do is I need to figure out a way to simplify number 4. Well, the easiest way I could do that is to actually work it out. So what I'm going to do is I'm actually going to plug in log for each of my y's and my x's, because technically that's what I did for the problem, right? I didn't take the y value and the x value. I took the speed, which is the x, and the distance that we took to brake, which is y, and took the log of each side. And by doing that, I can create this equation. Log of y equals 2.07 log of x minus 1.440. Well, now let's start to simplify. Let's see if we can turn this into something that we can actually use. So we're going to go ahead and use all of our properties. First step, I have a value outside. I'm going to bring it in. This becomes log y equals log x. This becomes the exponent of that value, minus 1.440. I can subtract that whole log of x value over to get log y minus log x, 2.071 minus 1.440. From there, subtraction, we can use properties to combine these two logs together. This would become log of y over x, 2.071. And that's going to be equal to 1.440. I can take this to a base of 10 on each side. This would cancel out the log, and I'm left with y over x to the exponent of 2.071 equals, and this becomes 0.036. And then multiply the x over to get y equals 0.036 x 2.071. So notice how, based off of my logs and doing my properties up here, I was able to retransform this into a true exponential equation. Sorry about that. A true exponential equation that we can use based on the situation, in which, instead of having to use my log values, I can literally plug in an x value and get a distance or a braking distance out from that. Now, that's a lot of work, right? And the thing about technology is we have options. We can actually try to do this or solve this out based off other pieces of information. So the whole reason we're doing this is because we want you to understand that linear regressions aren't the only thing we can use. We can use a power regression, okay, which would give us a function like this. Notice how similar this function or an exponential would be to this function over here, right? So what we can actually do is change how we plug this in the calculator. Let's just say I went back to the same data. So there's our linear regression. We talked about how that really doesn't help us too much. Well, what if we took the same values, we go to stat, we have the same values already plugged in, speed and braking distance, and we went over here and we did a power regression, which is all the way down at letter A. Well, if I follow the same path, notice what happens. My A value is 0.036 and my B value is 2.07. Well, that's awfully close to what we have over here. So just by using the calculator, we were able to get to the point where y equals 0.036x to the exponent of 2.07. So the thing that we want you to understand is that there's all these different types of regression based on the data you have. Okay. But now the important thing that we're going to have to be able to do is be able to determine, like, what type of graph do we have? Okay. So when I actually go back and actually look at this first function all the way at the beginning here, I want to look at this and say, okay, that is an exponential. So I want to use a power function to come up with that. Versus if I was given this graph to begin with, I'm thinking, okay, that's a linear function. I want to use a linear regression. So we have all these different types of regression that can actually help us out solve these equations. The only difference now is we have to try to be smart people and smart students and try to think, okay, what does this represent on the grand scheme of things? What graphs does it look like? What equation could this be similar to? Okay. And that's also why understanding like what your parent function graphs, kind of like what we do with transformations, are so important. If you can look at a graph and say, like, that looks like an absolute value function, that looks like this, that looks like this, then I know in the calculator which different types of regression I can use. Since I do have all these different types, I have a quadratic, I have a cubic, I have a quartic. Okay. Number 9 is a natural log, 0 is an exponential, A is a power function, B is logistic. So you have all these different possibilities, but we have to be able to understand which one to use in what time. Okay. But that's kind of the main idea of the whole lesson. Just being able to understand how to actually plug it in the calculator and go over regression. We'll be talking about this a little bit more in class the next day. But besides that, I will talk to you later.